Now welcome back. This is lecture 26. So we were discussing ways of mitigating distortion, and one example that I gave was that if you use negative feedback with high loop gain, then it is possible to mitigate distortion. Then I also said that having negative feedback with high loop gain for high frequencies is a difficult proposition, right? Which is correct. So that is why often you will see that negative feedback loops, especially negative feedback loops with multiple poles, are seldom used in RF circuits to mitigate distortion. However, there are certain class of circuits which also form negative feedback, but not in a very obvious way, which are often also used to reduce distortion, right? So for example, this is a topology that you might I am sure you are aware of. So let's say you have a source degenerated amplifier, and you apply an input here, right, as compared to the case where the source is grounded, and let's say you are applying an attenuated input here, right? So clearly in the case in the left hand side, or rather in the case in the right hand side, the VGS here is the signal directly appears at the VGS, but on the left hand side the signal appears between the VGS and the additional resistance, right? So essentially the VGS here is lesser with respect to the VGS on the right. Now it also depends on the amplitude of the signal, which I did not mention here, but from a very qualitative or intuitive argument, you can see that putting a resistor at the source is essentially reducing the VGS swing, not the quiescent VGS, right? If we can keep the quiescent VGS same, right, then in both cases, then the circuit on the left will see a lesser VGS swing, incremental VGS swing, than the circuit on the right. So given that we have what we know about the distortion producing mechanisms in our circuits, we understand that one of the primary reasons for distortion is the modulation of the VGS, which while giving rise to gain also introduces distortion. So we'd like to keep that modulation to as low as possible. So clearly the circuit on the left can give you a intuition that circuit on the left will have probably a better distortion characteristics, right? But however, there is a catch. It is not so obvious, even it is not generally true if you are limited with power supply, right? So if you are limited with power supply, let's say both of them are operating at a fixed power supply, then naturally in the circuit on the right you can possibly have a higher quiescent VGS, right, than the circuit on the left, because in the circuit on the left not only you will have to account for the drop across the resistor and the MOSFET, there is an additional drop you have to account for here, right? So which essentially means that for a fixed supply voltage, the MOSFET on the left will have a lower quiescent VGS than the MOSFET on the right? So even though sometimes an argument is made in the you will see that sometimes we make general arguments saying that a source degenerated MOSFET is reduces distortion, which the statement in itself is not incorrect, but given the constraint of a finite power supply, you will often see that is, if you will not be able to give a sufficient amount of quiescent VGS to that MOSFET, while with respect to a common source amplifier where you can give a higher amount of VGS. So this statement that, or this trade-off between design choice of just because at a 0th order it seems like a source degenerated transistor configuration can give you higher distortion, I choose that, it's not that obvious, right? The second problem that a circuit on the left can have is the fact that the amount of gain that you can get will be limited with respect to the gain circuit on the right, because gain is also a function of how much GM you can have, and GM is also a function of the overdrive, right? So in the best case scenario, the circuit on the left will have a GM of 1 over Rs, right? So in this case, if GMR or GMRS is much greater than 1, then the effective GM, then GM effective will be approximately 1 over Rs, right? But in this case, the effective GM is equal to GM of the transistor, correct? So as you can see that the effective GM that you are getting in the common source kind of configuration is also higher. So not only you are able to get higher quiescent overdrive, but also you are able to get a higher GM. Granted that at a face value it might look like the circuit on the right can have higher distortion, but it's not very, that statement has to be qualified with respect to a finite voltage supply that we are operating with, right? But having said that, there are some uses of this type of architecture. If you are using source degenerated architecture and you can maximize the VGS, then in certain cases there is sufficient amount of usage. One common usage is the narrowband LNA that we have studied so far, right? So again, what is the narrowband LNA? If you look at the narrowband LNA, so what did you have? We have this here. I am not showing the LG. So you have this CGS and we have this LS, right? And then you have all sorts of load. Maybe you can have a tuned load, maybe you have inductive load. Let's not bother about that. Let's only bother about the distortion in the current, right? So see, note that this is also source degenerated with an LS, but the LS is not having any quiescent drop, right? Because LS is not having any quiescent drop, you can have as much of a VGS that you would have quiescent VGS as you would have gotten in a common source configuration, right? So you can basically maximize the quiescent VGS and work with it, right? So if you maximize the quiescent VGS, which means you are maximizing the overdrive, right? So again, what does it mean? You are essentially operating at the maximum possible omega t or ft, right? And we have talked about this multiple times in this course. So again, to maximize the quiescent VGS, operate at maximum possible omega t, right? Again, why? Because you would like to, in order to get to maximum omega t, you are essentially saying that I am trying to get as much GM as possible with the smallest value of CGS, right? So when you say smallest value of CGS, which means the smallest value of W by L or W times L, if L is fixed, right? So for the smallest value of W, you are trying to get maximum GM. The only way you can do that is by increasing the VGS, right? So that translates to having biasing at maximum possible omega t. So you can see that this biasing at this omega t has so many benefits, right? So what are the benefits now? If you go back to the earlier lectures, biasing at omega t gives us very high GM. In this particular configuration, it gives us high gain, it gives us low noise, better noise figure essentially, and now we see that it also gives us better distortion performance, right? The only drawback is you will end up having a problem with the headroom, which essentially means that VDS nonlinearity, right? I mean, essentially when you have voltage swings here, so let's say you have voltage swings here. So clearly this transistor, you would want it to be operating sufficiently in saturation and not come close to linear, because the moment it now starts coming close to linear, what's going to happen? So whatever we have neglected till now, so we had this GDS. This GDS is also nonlinear, and the nonlinearity of the GDS will get magnified if you are biasing your transistor close to the saturation and linear region, right? So what is the intuition behind that? The intuition behind that is as follows. If you recall the IDS VDS plots of a MOSFET, so that goes something like this, right? Better MOSFET will have IDS VDS plot like this, and the slope of this is essentially the GDS. So naturally the slope here in this region is probably constant, which means you have kind of a constant GDS. But if a signal swings is pushing your VDS towards the knee of the plot, then the GDS also changes. So if the GDS changes with the signal swing, which means that your circuit is also nonlinear, right? So while maximizing the quiescent VGS helps in improving the VGS nonlinearity, it can have detrimental effect on the VDS nonlinearity, right? Maximizing the quiescent VGS helps in improving the GM nonlinearity, but it can have a detrimental effect in the GDS nonlinearity, right? So a best case scenario is you'll have to do a similar analysis just like we did for GM for the GDS also, right? And then you bias your circuit in such a way that none of them dominate, or both the GM nonlinearity and the GDS nonlinearity are kind of giving you the similar amount of distortion, and that is probably somewhere you would like to bias your circuit. And however, in most cases, designers we resort to simulation in these cases, right? Because all these hand wavy small second order distortion, the second order equations, or even slightly even equations having G3 are not sufficient for analyzing MOSFETs in a brute force manner. So for that we had to resort to circuit simulators, and in that case what we do, we basically you try to bias your circuits, bias your transistor to as high a GM as possible, or as high a VGS, quiescent VGS as possible, and then you run your simulation, and then you check whether the output is and then check that if you keep on increasing VGS after some time, right, after some value of VGS, you are not going to see any improvement in the distortion numbers, and it will also start getting worse, right? At that time you know that you are being dominated by the GDS distortion, GDS nonlinearity, and there you stop your sizing, right? So that gives you kind of an idea of how to bias these transistors, these type of LNAs for as high a distortion performance as you want it, right? Okay, so given that till now it seems like negative feedback cannot really solve the problem because of reasons that we have talked about. The only handle seems to be to increase the VGS, quiescent overdrive. Then it might seem that we have very limited options to improve the distortion performance of an RF amplifier, right? It might seem so, but that's not the case. So what I'm going to do for the rest of this lecture is to run you through some of the techniques that are used quite often, and most of the techniques that I'm going to talk about are available in this paper. This is a tutorial paper. The details are here. You can go through it. I'll cover a couple of them which has been enumerated in this paper, but there are more ways of linearizing. However, most of them fall into one or two similar categories, and there are variants of those categories. So what I'm going to do now in the remaining part of this lecture is to motivate some of the basic ways of at least basic ways of mitigating distortion, right? Okay. So negative feedback doesn't work. So feedback doesn't work, and if you recall, I ended the last lecture by saying that if feedback doesn't work, maybe feed forward can work, right? So that was a off the cuff remark, but if I have to if we have to make it work, we have to be slightly more analytical, right? So in order to do that, let's assume that we have a block which is nonlinear. Obviously, you have to assume nonlinearity, otherwise there's no point in discussing mitigation of nonlinearity. And for the time being, let's assume that I have only third order nonlinearity, because if I take differential, the second order goes off. So let's say I have only a third order nonlinearity, right? So which means that I have the fundamental, which is A1 times VI, and I have a third, which is A3 times VIQ, right? Okay. So what am I having? I have a VI here. Here I have A1 times VI plus A3 times VIQ. So if I stare at it for some time, you see that if I apply, let's say, VI over 2, or rather if I apply alpha times VI to the input, the output will be alpha times A1 VI plus A3 times alpha cube times VIQ, right? So it seems like the fundamental term, it doesn't seem like, but it is evident from here that the fundamental term and the distortion term are scaling at a different rate if the magnitude of the input scales, right? And that should be evident by now, because the metrics of IIP3 and IIP2 and all those things essentially leverages this fact that the distortion terms they increase at a faster rate with respect to the fundamental as the input amplitude also increases, right? So now, given that we have this observation, is there something that we can do, at least mathematically, to get rid of the distortion term? As you probably can readily imagine, the fact that if I give, let's say, we give two different inputs at two different instances, right? So I am going to get one fundamental term here and one distortion term here, and another fundamental term here and a distortion term here. But the fundamental and the distortion terms are not scaling equally. So there seems to be a window of opportunity to treat the fundamental and the distortion terms separately, right? Maybe I can cancel out the distortion term and not cancel out the fundamental totally, right? So let's take an example. Let's say alpha is 1 by 2. Let's say I attenuate VI, right? So let's say I do VI by 2. Instead of VI, I apply VI by 2, right? What do I get at the output? I will get A1 times VI by 2 and A3 times VI cube by 8, correct? So what if I then take this output and take these output, right? And let's say I take this output, multiply it by 8, right? So what do I get? An ideal multiplier of 8, right? Again, you might say that how can I get an ideal multiplier? We'll talk about that, right? So let's say we have an ideal multiplier of 8. So what do I get what do I get as the output? I get why 8? Because ultimately I want to cancel out a3vi cube term, and the top term has a a3vi cube. So if I multiply by 8, maybe I can do something. So this becomes 4a1 vi by 2 plus a3 vi cube by 8, right? So now if I take this term and take this term and subtract, what do I get at the output? I essentially get minus 3a1 vi by 2. There is no distortion term present, right? So you might say that this is probably an algebraic trick, but ultimately how do I go about doing this? So let me show you a quick example of how can you do about doing this. So let's concentrate on the fact that we are only trying to mitigate the distortion arising of VGS nonlinearity, that is a GM nonlinearity, the nonlinearity of the output current, not the GDS nonlinearity per se, right, for the time being. So let's say I have a GM which is distorted, right? So if I apply Vi, the current that comes out is GM times Vi plus G3 times Vi cube. Okay. So let's say this is, let me only show a single-ended equivalent, so that the representation becomes easier. And you can assume that there is a differential circuit equivalent of that, right? So what do I need to do? I need to attenuate Vi by a factor of 2, right? So how do I attenuate Vi by a factor of 2? Simple. I do a resistor divider, but maybe resistor divider, one might say that it's going to consume, not consume per se, but it can contribute to noise, right? So I can do a capacitor divider, because note that we are operating at RF frequencies, right? So capacitors are also give, they don't really give you really open circuit, right? They have fairly low impedances. They can have. This is C, this becomes Vi by 2. So what else do I need to do? So this Vi by 2 I need to apply to the same GM, right? So now I cannot apply it to the same GM. What I can do is I can have a copy of the same GM, right? So let's say I copy the same GM. If I copy the same GM, what will be the output? Here the output will be GM Vi by 2 plus G3 Vi by 2 whole cube, that is G3 Vi cube by 8. And then I have to multiply this current by 8x, right? So how do I multiply current by 8x? What we can alternately do is, basically you have to copy the same circuit 8 times and add up current, right? So how do I copy how do I essentially add up currents? If you have current sources, right, these are all voltage controlled current sources. If you have current sources, you basically join the outputs of the current sources together and you add up currents. So what do? You copy this thing again 8 times, right? So this is 1, this is 2, 8. So you have 8 copies of this, and join all of them together. So what will be the output? The output will be 4 GM Vi plus G3 Vi cube, right? And then what do? So you subtract these two, right? So how do you subtract? Now you might say that Now in order to subtract, I need another amplifier maybe, but note that not necessarily, because if you have access to both the terminals of if let's say you have a differential implementation, let's say we have a differential implementation, otherwise you are going to have a second harmonic term, right? So if you have a differential implementation, which means that there is a negative terminal that is available to you, so you can basically add up the negative terminals. Alternatively, if you do not want to do that, so you can then say that I will flip the terminals of the input here. So the current here is in this direction, Gm times Vi plus G3 times Vi cube. So if I simply connect these dots, connect these wires, the output current that is going to come out will be 3 Gm times Vi, right? So this has no distortion terms, right? So 0 times Vi cube. No third order distortion term, right? So this is another way of, this is basically a technique which is cancelling distortion by feed forward way of cancelling distortion. Okay, so by doing this, I mean, if you have differential and you have this, then obviously you are able to cancel out both the second and the third harmonics. But I mean, as you can see that you end up having, instead of having, but the key thing that you have to ensure is that all these GMs are identical. When I say identical, I mean they are biased identically, right? They are in the layout also, they are placed very close to each other. That is, they are as close a replica of the original GM as you can possibly have. But then what's the problem? The problem, you see that earlier you were burning, in this case, if you are burning in one GM, if you were burning P amount of power, now you are burning P amount of power in 1 plus 8 GMs. So essentially you are burning 9x the power, right? You are burning 9x the power. But is that a bad thing? What is happening to the signal? Right, the signal was Gm times Vi. The main signal is Gm times Vi, but now the main signal is also 3 Gm times Vi. So essentially you are getting, in terms of power, signal power at the output, you are getting 9x, right? So you have increased the power dissipation by 9x, but the signal power has also gone up by 9x, and the distortion has reduced, right? But even then it's not a sufficient, even then it's not a analysis that is fully complete. What you have to do is to find out the noise of this configuration also. I'll not do it for you, but you can do it yourself. It's quite trivial. You find out the noise for, assume that certain amount of noise from one OTA, one GM. The same amount of noise will come down from all the other GMs, and you can add them up and then see, right? So as it turns out, this works, but I mean, the sheer amount of power that you have to burn sometimes can become prohibitive. The other problem of this architecture is, if you implement it in this way, is that what happens to the other nonlinearity? I understand that second order goes off, and the third order also goes off. Fourth also goes off because of distortion, because of differential implementation. But what about fifth? As you will see that the fifth will get amplified. If you have a term which is G5 times Vi to the power 5, so that is not getting attenuated, right? That can get amplified. So that's one of the problems of this type of architecture. So in the paper that I have shared, right, in the tutorial paper, if you can go through it, you will see that if you have access to it, it's not mandatory that you go through it. I mean, nothing in the paper that you will see will be a part of, I mean, that thing in the paper that we have in the paper, but not in this course, it will be a part of any of the exams. But if you have access to the paper, you can go through it, and you'll see that there are some other architectures which are variants of this, which can also play around and maybe cancel other other harmonics as well, right? Okay, so this is one way of going about mitigating distortion. uh, there is another very popular way of, or I mean a very cheeky way of mitigating distortion. This is particularly true for MOSFET circuits, right? Not necessarily for BJT or other kind of circuits. But note that this way of mitigating distortion is true for any type of circuit. We did not assume any did not assume any sign of GM or G3 or anything. It's a generic way of mitigating third harmonic, right? But or rather the cubic nonlinearity. I should not say third harmonic necessarily. It's a generic way of getting rid of the cubic nonlinearity. However, there is one technique which is particular to MOSFET, and that is what we are going to see next. Another technique that you would find in that paper and also in certain textbooks which are used for linearization purposes, and this technique is particular to MOSFET, not for any generic device, is the following. So when a MOSFET is biased in saturation, right, so what we see, from whatever discussion we had, we saw that it's a compressive nonlinearity, right, with regards to if you keep on increasing the if the signal swing keeps on increasing, then ultimately things will get compressed, right? So it is expected that G3 will have opposite sign of GM, right? So in a MOSFET, biased in saturation, GM and G3 have opposite sign. Okay, so this is basically one way of saying that this is compressive nonlinearity, which is intuitive, right? But what is not intuitive is if you MOSFET, if you bias it in weak inversion, right? But in inversion, the current voltage characteristics of the MOSFET is similar to that of a BJT that you have. That is, your ID is proportional to e to the power VGS over threshold voltage. Then you have some additional term, but it is proportional to this. Okay, so which essentially means, sorry, not threshold voltage, over VT. Okay, so where VT is KT over Q is 26 milli electron volt. Then you have some other terms, but the key thing to note here is that if your ID is proportional to e to the power VGS, which means all the derivatives, right, with basically IDS, dou IDS, dou VGS will all be positive, right? So i.e. GM and GDS or GM and G3 have the same polarity. This is something that you can verify. You can take, if you have access to MOSFET PDGs, right? You can take a MOSFET and plot. So basically, you plot IDS versus VGS. Basically, you should look something like this, where maybe your threshold voltage is somewhere here, right? So this side I can say is subthreshold. This plot is for VDS greater than VGS minus VT, right? And this side you have saturation, inversion and saturation, right? So if you do that and then you differentiate this plot to get GM and G3, what you are going to see is that if you plot G3 with respect to VGSQ, this is VGSQ, let's say, you are going to see a plot like this. So we expect the G3 to be negative because of a compressive nonlinearity, which means we expect G3 to be somewhere here, right? But you will see that because of the exponential characteristics of a MOSFET in subthreshold, you are going to see something like this. It is the G3 is positive, it rises, and then it dips, and then it goes negative. So the exact value of the or the exact shape of the curve is not of that much of importance, but the part that is important is to understand that G3 changes polarity. Now, why is that information important? This is important because if G3 has to change polarity, then which naturally means that G3 goes to 0, right? So there will be some sweet spot. Let me call this VGS3, where G3, so at VGS3, G3 equal to 0, right? So the value of the this point VGS3 can vary based on your biasing, based on the devices and so on. But the key thing to note is that in a MOSFET, you are going to find a point, a VGSQ, where the G3 term effectively goes to 0, right? And this will be somewhere at the borderline of subthreshold and inversion. So this will be somewhere around weak inversion regime. Right? So for circuit designers' point of view, how does it help us? It can help us because if I can identify this bias point, right? I ran a sweep of VGS, parametric simulation of VGS versus G3, and I found out that point. So near about that point, I can bias my transistor. So I ensure that the transistor is biased at that, I mean, with whatever your favorite biasing technique. Let's say, I mean, you push in a current and you bias it with a constant current source. Then you have this. Then you have this, and you feed in your signal. I'm not showing matching and all. I assume that those things are taken care. So, which means that ideally, if this transistor, if M0 is biased at VGS3, i.e. G3 equal to 0 point, then M1 will also be biased at G3 equal to 0, right? So, but this makes an assumption that M0 and M1 are identical. Even though they might be identical in terms of their W by L, their VDS is not identical. So you can have some problem. So if you want to make it a better matching, so the thing that we can do is similar to whatever we do it in analog circuits, is you put in a gas code, right? Similarly, here also we know that generally we are going to have a gas code, right? Not necessarily for matching purposes, but for other kickback and distortion and gain performances, right? It's better to have a gas code. So VGas, this is VGas, right? So if I bias it like this, and I ensure that M0 is also biased at G3 equal to 0 point, then M1 will also get biased at G3 equal to 0 point, and will be fine, right? So this is actually used, right? But there are some issues with this architecture also. As you can see, one problem is this Z3 equal to 0 point is a very sweet spot, right? If you go slightly this side and that, then you either have you essentially get non-zero G3, and as it turns out, this the slope of this G3 around the G3 equal to 0 point is actually not that flat, right? It's quite steep, which means that if you make an error in estimation, there can be a lot of problems, which means that there has to be a lot of trimming and calibration circuit. There are architectures and patents who work on making sure that your circuit actually gets always biased at G3 equal to 0 using some replica based negative feedback mechanisms. But the key point is to notice that if you actually plan to design your circuit leveraging this G3 equal to 0 feature of MOSFET, then you need to have some way of ensuring that across variations of process, across variations of temperature, where this curve can also move around, you have to ensure that you always bring that your bias point back to G3 equal to 0. Otherwise, you are going to have, you can end up having a very bad distortion, right? Because you might, if you somehow end up biasing your circuit here or here, then the whole purpose of using this mechanism is lost, right? An extension to this is also, there are research papers who have published this type of architectures. An extension to this is also, okay, by the way, before I move on, so what this term does not show is what is happening at G5, right? As it turns out, if your signal swing is large, right, which means that you are not necessarily only swinging around G3 equal to 0, you are swinging quite a lot away from G3 equal to 0 point also, right? If your signal swing is large and your signal swings this by a considerable amount, which means that you are also not only your signal is not limited to the G3 equal to 0 sweet spot, it is experiencing a large variation of G3 also, right? Which essentially means that variation of G3 means you have higher order derivatives on G3, which means you have G5. So which means that when you have large signal swing, the G5 distortion kinds of starts dominating and so on, right? So even though this kind of topology works in certain cases, but you have to be careful with regards to the amount of signal swing that you can experience. And now, having said that, an extension of this topology is also something that is called a derivative superposition. But without going into the terminology, what people tend to do is to instead of having one transistor which is trying to, where you bias your LNA for G3 equal to 0, because if you bias your LNA for G3 equal to 0, you are not having a particular control over GM, right? You would like to have a control over GM while making G3 equal to 0, right? So which essentially means that you have one main transistor for which you decide your GM a priori, and you do not bias it with any G3 equal to 0 point. It is in saturation with the GM that you want, right? So let's say, you have matching network and all, I'm not showing that, but let's say this is some GM and it has some, you have some GM and you have some G3, and let's say for the GM that you have, your G3 plot, or rather your G3 plot looks like this. This is M1, this is G3, this is VGS for M1, and let's say you have biased your M1 in such a way that you did not bother about where G3 is, you wanted to maximize GM, and for that maximized GM, you let's say you biased your, this was your VGS VGS1. Okay, so clearly you have non-zero G3. So what you can do is have another transistor, right? Have another transistor. So what you can do, you can have another transistor which is biased in such a way that its G3 positive value superimposes on top of the negative value of of this G3, right? So let's say I have another transistor which is which has similar characteristics, but this one is biased. Let's say I call this VGS2, and this one is biased at somewhere here. This is VGSQ1, this is VGSQ2. So if I add up these two currents, then the G3 for this is negative and G3 for this positive. So if I add up these two currents, then around that bias point they can cancel off, right? And in this case you are not really compromising too much on the GM, because naturally for very small VGS2 the GM of the second transistor will be minimal, right? So the GM of the total transistor will be dominated by the effective GM will be dominated by the first transistor, and the second transistor GM will not get dominated as much, right? So how would you go about biasing this scheme? So let's say this is M1, which has the dominant GM. Let's say I call this GM large, and G3, which is negative GM, negative G3, and you bias it. Let's say I am showing the most trivial type of bias. Let me call this R1, R2, and this is large VGS, right? This is biased at VGS1. Okay, then you take another transistor. Let's call this M2, and this, let's say you bias it at, let me call this R3, R4, and you bias it at VGSQ2. So the first one was VGSQ1, right? So the current that is coming out of this, I mean, or rather, I mean, if I write it in this manner, so this current is GMVI plus G3 neg VI cube, and the current that is coming out of M2 is some GM small VI. So this is GM large VI plus G3 positive times VI cube, right? If I ensure that both of them are seeing the same VI, how can I do that? I can basically AC couple both their inputs together. All I have to do is to add up these two currents. How do I add them up? I connect them directly, right? So if G3 positive VI cube is the same as G3 negative VI cube, that let's say you have characterized your transistors and you have found out, then naturally this current, right, will be, I mean, assuming everything is biased, the drain is biased and everything, this current will be GM large VI plus GM small times VI, right? And there will be no G3 equal to 0 term. And not only that, as it turns out, if you do this, you will see that the range for which this cancellation happens is slightly larger than the case where you only bias it as a sweep point, right? This type of technique is often called derivative superposition, because you are essentially biasing two transistors which have different third order derivatives, and you are trying to superpose their characteristics, right? Okay, fine. So there are n number of ways of picking and choosing different types of techniques, right? Sometimes feedback, sometimes feed forward, sometimes this derivative superposition, and so on. There are many ways of trying to mitigate distortion, right? It's not possible for me to cover everything, but hopefully you got a flavor of how to go about designing an LNA in order to in order to ensure that not only you honor matching and you reduce you get gain and you reduce noise, but also simultaneously use mechanisms to reduce distortion, right? So what I'll do is I'll stop the discussion on distortion and LNA here, and we'll given that we are two-thirds through the course, I would like to steer into something else which we have not focused too much. That is, I'd like to go into discussion on some important passives, right? So for example, I have been talking about inductors and capacitors and resistors and as if they are ideal, but as it turns out, when you are doing integrated circuit design, there are not a lot of non-idealities with respect to these passives that we have to deal with. We'll talk about some of them and some circuit techniques and some layout techniques in the next class, right? Okay, we'll stop here.